identifying redox reactions. Let's look at how. You can do this by using oxidation number. So this stands for oxidation, okay? So you can use oxidation number to identify redox reactions. Obviously this here stands for reaction, by seeing if both oxidation and reduction, okay, so this is oxidation and reduction, are occurring simultaneously. Through the transfer and receiving of electrons. This stands for electrons. Let's have a look at an example. So in this example, we're trying to figure out which of the reactions below are redox reactions. Okay, so this is just the first one here. We're going to decide whether this reaction is a redox reaction. Again, we have to create the oxidation number. So of course, this here is a free element. So if it's a free element, it has an oxidation number of 0. This one here is also a free element, so this also has an oxidation number of 0. How about this one over here and this one over here? Well, again, oxygen tends to be a oxidation number of -2. So we have 1 oxygen, so 1 times -2. And the whole thing would have to equal 0 because we don't have a particular charge for this H2O molecule. But also you have to remember that there are 2 oxygens, right? The coefficient of there is a 2. So technically, we got to do this -2 times 2. So that would give us -4. Okay, so I've written that over there. So what number does this number have to be? Well, this was a 2, and we know that hydrogen, it's a group 1, so of course it has to have a charge of 1. So if we put a 1 over there, we have 2 times 1, which will give us 2. But also this 2 needs to multiply by that 2, so that will give us a 4. Does it work out? Absolutely. 4 minus 4 gives you that 0. So 1 up there is suffice. So as you can see, this has an oxidation number of 1, and this has an oxidation number of -2. If we were to look at the oxygens, this here is a 0, and then it went towards a -2. Is that a reduction or is that an oxidation? This is obviously a reduction. It got reduced. Okay, so of course this gained 2 electrons. How about this one over here? Well, this 0 went over to that 1 over there because this is a hydrogen, this is a hydrogen. What happened there? This is oxidation because it increased an oxidation number, so we lost 1 electron. So do we have oxidation? Yes. Do we have reduction? Yes. So because we have both of these occurring simultaneously, this would be a redox. Therefore, yes, this is redox. So let's look at the oxidation numbers. This whole thing needs to equal 0, right? So 3 times, again, -1 tends to be the charge for the chlorines. They are a group 17. So 3 times -1 gives you that -3. Okay, so what number does this have to be to plus -3 to give us 0? Obviously a 3. Okay, so this would be a 3. So now let's try this H2O. There's 1 oxygen. It tends to be a charge of -2. So 1 times -2 will give you that -2. But remember, this -2 needs to multiply by that 3 over there. So 3 times -2 gives you that -6. Okay, and obviously this whole thing here needs to equal 0 because there's no charge around this whole compound of H2O. So now this obviously needs to be a 6, right? Because 6 minus 6 gives you 0. So how do we get that 6? Well, we have 2 over here. 2 times what? Times 3 will give you 6. Obviously a 1. Okay, so 2 times 1 gives you 2, times 3 gives you 6. So 1 here would be the oxidation number. Now let's try this one over here. So this again tends to be a charge of -2, so 3 times -2 gives you -6. The whole thing needs to equal a 0 because there's no particular charge for the whole compound. Again, we know that this is typically a 1, so 3 times 1 gives you that 3. So 3 plus what? -6 will give you 0, obviously a 3. Okay, so we've got to be putting a 3 up there. There's only 1 phosphorus. Okay, so 3 times 1 will obviously make this a 3. So this is good. 1, 3, and -2 are the oxidation numbers. Let's try this hydrochloric acid over here. This needs to all equal a 0, no particular charge for the whole compound. Chlorine tends to be a charge of -1, so what's 1 times -1? That's -1 times 3 gives you that -3. Okay, so what does this oxidation number have to be? Okay, there's 1 hydrogen, so 1 times what? Times 3 is going to give us 3 because we want 3, right? Because 3 minus 3 gives you that net 0, okay? So obviously this here has to be a 1 because 1 times 3 will give you that 3. So 1 and -1 are the oxidation numbers. So let's look at our phosphoruses over here. They look the same, nothing's really changed. How about our chlorines? Okay, we have got a chlorine here, nothing's changed either there, okay? There's -1 and -1, okay? So what else do we have? Well, we have hydrogens, this is a 1. How about this hydrogen over here? That's a 1. This hydrogen here with this hydrogen here, that's also both 1s. So nothing's really changed. And how about oxygen? This used to be a -2. How about this oxygen? Also a -2. So nothing's really changing. There is no transfer of any of the electrons. So therefore, there is no redox. Okay, we don't see any oxidation. We don't see any reduction. Again, we have a charge of -2 usually for the oxygen. So 2 times -2 gives you -4. Times that 3 gives you the -12. Right, the whole thing needs to equal 0, obviously, okay? So again, what does this number have to be? Well, there's only 1 nitrogen, so 1 times what? Times 3 is going to give you that 12, obviously a 4, okay? So 4 and -2 are the oxidation numbers. Let's try this H2O over here. Again, 1 tends to be a charge of -2, so 1 times -2 gives you that -2. Whole thing needs to equal 0. What does this number have to be? Well, there's already 2 of them, so 2 times what is going to give us that 2? Obviously a 1, so oxidation number is 1. Let's try this one over here. Tends to be a charge of -2. So 3 times -2 gives you that -6, right? But -6 needs to times that 2 over there, so that gives us a -12. Again, whole thing needs to equal 0. Again, this hydrogen here tends to have a charge of 1. Okay, so 1 times 1 gives you 1, times 2 gives you that 2. Okay, so 2 plus what number? -12 will give you that 0. Obviously, this here needs to be a 10, okay? Because 10 plus 2 will give you that 12 to -12 to give you that 0. So how do we do this? Well, we have 1 nitrogen. We have to multiply by 5 up there because once you times 5, you then have to times 2, which gives you that 10 over there, okay? So 1, 5, -2 are the oxidation numbers. And this one over here, typically a charge of -2. So 1 times -2 will give that -2. Whole thing needs to equal 0. So what does this number have to be? Well, this here obviously has to be a 2, right? So what 1 times what number will equal 2? Obviously a 2, okay? So 2 and -2 are the oxidation numbers here. So let's look at our nitrogens. Bring our nitrogens over to this nitrogen over here. What do we have? Well, we have 4 to become a 5, right? So this is obviously an increase in oxidation number. So this is oxidation, okay? There is a loss of 1 electron, but guess what? There's another nitrogen over here. What's going on? Okay, so let's bring this nitrogen all the way to this nitrogen over here, but as you can see, it is being reduced. Okay, it's getting smaller, so there is a gain. What is the difference between that 4 and 2? Obviously a 2, so it gained 2 electrons. Interesting. Okay, what else do we have? Well, we have oxygen over here, so this oxygen to this oxygen, it's just from -2 to -2, so nothing really happens. And how about this oxygen all the way over to this oxygen? Same thing, we're just going from -2 to -2, so nothing's really happening. So as you can see, we obviously have a redox reaction, okay, because we have reduction and we have oxidation. Put those things together, we get that, right? Redox. However, it's happening with the same element. Okay, so atoms of the same element are both doing oxidation and reduction. So this here would be disproportionation, okay? Right, so that's the answer for that. In case you're still confused about disproportionation, I just did a video on this previously. Please have a look at the link in the video of the description. to have a more in-depth explanation and analysis of this. Well, let's have a look at this question here. How do the oxidation numbers differ from the numbers that are used to indicate charge? Well, you're probably used to seeing, for example, if we have potassium, it tends to have a 1 plus charge, right? Why was it always written as 1 plus instead of plus 1? Because this plus 1 is related to the oxidation number that we've been doing in the series, okay? When you have a 1 plus written where the number comes first and then the plus comes after, this tends to be for the charge, okay? So what is the difference between the two? For oxidation number, its number is usually the same as the charge, but only if it were to be completely held by the most/largest electronegative atom. Charge, however, is represented, so REP stands for represented. It's represented by the amount of electrons it wants to take away or gain. To become stable. If you were confused about electronegativity over here, please see the video link in the description where I go into an in-depth explanation about what electronegativity is. And lastly, let's have a look at this question over here. Under what circumstances does the oxidation number of an atom in a compound appear to be a fraction instead of an integer? Well, let's have a look at an example here. So let's use Fe3O4 as an example. So this tends to be a charge of -2, right? So 4 times -2 gives you that -8, and this whole thing needs to equal 0 because we don't have a charge for the whole compound, okay? So what number minus 8 is going to give you 0? Obviously an 8, right? So 3 times what number will give us that 8 to subtract that 8? Obviously, it's not a very clean number, so we can just put here in brackets 3 times whatever that number is minus 8 will give you that 0. So now we just have to isolate for our question mark here, okay? So we can just bring this over to the other side, or if you want to be more concise, we can add plus 8 over here, so the cancel out, okay? So if you do it on the left side, you got to do it on the right side, so we're going to add 8 over there, so we got 3 times the question mark is supposed to equal 8. So how do we now isolate for our question mark here? Well, what's the opposite of times 3? It's obviously divide by 3. So these go away. If you do it on the left side, you got to do it on the right side. So our answer ends up becoming 8 over 3. Okay? So why is this turning out to be a fraction instead of an integer? The reason is because it should actually be, so this thing over here, it should actually be Fe2O3 with FeO, okay? So this means this iron here, it tended to have a charge of 3, right? A 3 plus charge, because this 3 went all the way down here, and then this 2 came from that -2 up there, okay? So this here was technically iron 3. This one here, however, again, this tends to have a charge of -2, right? So this -2 went all the way down over here, and then this must have been a 2 because that also went down there, okay? Why? Well, if this was a charge of -2, and if this was a charge of 2, what would happen? This would come down here, this would come down here, then they go away. Then of course you can simplify this as 2 divided by 2, that would just give you 1, right? Alright, so that's typically what we have right now. So this here must have been iron 2. In cases like these where we have multivalence involved, this can actually make it a lot more complicated, okay, and give us a fraction. But just for simplification purposes, this and this were combined together to look as if it was just Fe3O4, right? Because again, there's 2 Fe's over here, there's 1 Fe over there, so that becomes a 3. There's 3 oxygens over here, there's 1 oxygen over there, so then this typically becomes 4, right? So if you add them all up, it kind of looks like that, but that actually isn't the reality. In some cases, however, the carbon could become a problem, okay, because obviously on our periodic table it's right within the group 14, which means that it can either gain electrons or lose electrons, right? So let's have a look at how this ends up becoming a problem. Well, we have this whole thing needing to equal a 0, right? And then there's 1 oxygen, so this is typically a charge of -2. We do 1 times -2 will give us that -2. Okay, and this here tends to be a a charge of 1. Okay, so 6 times 1 gives you that 6. Okay, so what does this number have to be to add 6 minus 2, which is just 4, to equal 0? So we got to do 3 times what number plus 6 minus 2 is going to give us that 0. Okay, so we got 3 times that question mark. This again is a plus 4. We can minus 4 over here so that they can cancel out. If you do it on the left side, you got to do it on the right side. So there we have that. So we got 3 times that question mark is equal to that -4. So to isolate this, we just got to divide by 3 because this is multiplying by 3. So if they're opposites, they cancel out. If I do that on the left side, I got to do it on the right side. So this question mark is going to equal -4 over 3. As you can see, we have gotten a fraction instead of an integer. So these are the 2 green questions of the day. This here is the first one. This here is the second one. Please try this on your own. Pause the video and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.